Okay, let's start. Is my screen visible to you? Can you see my screen?
Yes, sir, it is visible.
Okay. Okay. So today, what we'll be doing is separation of two miscible liquids in a seed plate distillation column. So in the last lab was on batch distillation, so it's on continuous distillation. Okay, and there is one more difference. Here you will be doing separation of a binary mixture in a multi-stage seed plate distillation column. So why multi-stage is necessary? Just recall what we have done last time, uh, or recall the definition of the distillation, which is basically preferential separation of more volatile component. So if you have a binary mixture where the volatility of these two components are different, that means they differ in boiling points, and wider the difference, the better is the separation. So when you have such a binary mixture, and if you vaporize the feed solution, if you vaporize the feed solution, partially vaporize the feed solution, and this liquid and vapor, these two streams come in direct contact with each other, let the equilibrium be established, and then you vapor part you condense. You can take out the vapor part and condense it. So you have basically now two different liquid mixtures, and they will be differing in concentration. The condensed vapor will have more volatile components in it compared to the other part. So basically what you have done is you have done some kind of separation, but you can imagine well that this separation will be limited. So to improve the separation, what you need to do is you need to repeat these in suitable devices again and again. So these suitable devices are nothing but what we call tray in a tray distillation column. Okay. So basically you need to bring in this liquid and vapor in direct contact with each other again and again. Okay. So continuously they will be in contact with each other, but stage wise in a tray distillation column. There is another way of bringing these two phases in contact with each other, that is in a packed bed distillation column. So we will not be talking about that. We will be talking about only the tray distillation column, and particularly sieve tray distillation column. So just for the sake of completeness, what you see on the right hand side is basically a packed distillation column. Okay, so inside basically they are packing materials. Okay, they do the job of these trays in a distillation column. Okay, now here so let us focus our attention on this. So I'll just go through the nomenclature for the you know uh, for the benefit of this presentation. Okay, so we have tray distillation column, meaning that we have these devices which we call trays, which are nothing but devices for bringing a liquid phase and vapor phase into intimate contact with each other, so that mass transfer takes place between these two vapor and between these two phases. And so in this distillation column, the what you see are the key aspects of a distillation column. Okay, this is just textbook description of a distillation column. You have this feed. So let us consider I have a binary feed A plus B. A is more volatile than B. That means A has is volatility is much higher. It's a less boil. It has less boiling point than the B. Okay, so the feed enters somewhere in the middle of the distillation column. Okay, and you see at the bottom there is a reboiler. So the feed will come to the okay. The feed may be of different types, right? Feed may be a liquid stream. It may be partially vaporized. It may be saturated liquid, so on and so forth. Let us consider feed is a just liquid mixture. Okay, binary liquid mixture. Maybe unsaturated. So when the feed enters through the distillation column, it's a liquid mixture. It comes down due to gravity. Okay. So it flows, basically it flows through these plates. Okay, so like it will flow through this plate like this, and then it will come like this. Again, it will flow like this. Again, it will come like this. Okay, and through these perforations, the vapor will come out. Where this vapor will come from? So the liquid goes down to the bottom of the distillation column. Then you see there is a reboiler, which is nothing but a heat exchanger. So it partially vaporizes this liquid from the column and send the vapor back to the distillation column, which again, because it is vapor, it goes up. So when it goes up, it passes through these perforations on the trays, and the liquid is, flowing across these trays. So the vapor passes through these holes, and during that, it passes through the liquid pool, small liquid pool that is being maintained on these trays. So during that time, you have an intimate contact between liquid phase and vapor phase. So what is happening is the vapor will become richer and richer in more volatile component as it goes up, and the liquid, so it will be stripped of the less volatile component. So liquid that comes down will be richer and richer in the less volatile component. So vapor will be more and more richer in more volatile component. That means component A. So when the vapor comes out from here, it will be richer in A. So that you condense, and then that condensed liquid is your product. Okay, but what you do is part of this liquid you send back to this distillation column as reflux. You know that we call that as reflux, so that that vapor that goes up beyond the feed tray, okay, gets a liquid stream for doing this mass transfer. Okay, so note that here the vapor that goes up, okay, gets a liquid stream from which is coming from the top as well as which is coming from this feed for mass exchange to take place. And for this part you need a liquid stream for causing the mass transfer with the vapor that goes up. So what you do is you send back this reflux, send back this part of this condensed product, which is quite rich in A, as reflux stream. Okay, so this is known as rectification section and this is known as stripping section. So here basically, okay, so the part above this feed we call as rectifying section. The part below the feed we call as stripping section. So the tray over which this feed enters we will call this feed tray. Okay, so I think you, since you have done this course already, you'll be able to recollect these nomenclatures. Okay. So this is what actually happens. You have these trays, okay, with perforations in it. Okay, so the liquid comes from the plate above it, flows down like this, goes to the next plate, flows like this, goes to the next plate, so on and so forth. Okay, and the vapor passes through these perforations. Now, there are few things like look at this part. Okay. Uh, this is look at this part. This is known as wear. Okay. So the liquid comes through this. This is known as downcomer. So liquid from the top plate flows through this downcomer, and then you see there is a gap, so there is a downcomer clearance. Then the liquid flows like this, flows across the plate, and you see there is an obstacle here which is known as wear. So this will help you to have a liquid pool of this depth, so that the vapor that passes through, vapor can pass through a pool of liquid which is actually flowing like this. Okay, so you can see it here. So up to this level, a liquid height will be maintained. So flows through this downcomer and then passes like this. Okay, so what we have in our laboratory is a sieve tray distillation column. Okay, so sieve tray is one of the simplest trays. So it's nothing but a perforated seat. Okay, so it's an horizontal perforated seat with wear on one side, and you see that schematically this is how this vapor will pass through. Okay, so there will be a liquid pool over here, so vapor simply passes through like this. This is an image of the sieve tray. It's simply perforated plate. Note that there will be a small pool of liquid over this. That is because of this wear. Now, there is another very popular tray known as bubble cap tray. Okay, here which actually is more efficient, which in terms of exchanging mass with the vapor phase and the liquid phase. So a number of small caps are mounted on a riser. Okay, so these are those small caps, bubble caps. Okay, they are mounted on this riser. So these are the riser. Okay, so you can see what happens is the vapor passes through. Okay, the vapor goes through these perforations and then is forced to go down like this and then goes through pool of liquid and comes out like this. Okay. So this is the vapor flow. It is same as this. Okay. So you have a better mass transfer here. Anyway, let us we'll restrict ourselves to sieve tray only because we have the sieve tray distillation column in the lab. Another two things, please take care that when the vapor passes through this phase, okay, the flow rate is important. Vapor flow rate is important. Okay, the vapor flow rate should not be so low that liquid comes down through these perforations due to gravity. If that happens, that is known as weeping. Okay, so this weeping causes, you know, that you are basically compromising with mass exchange. So basically that will lead to loss in tray efficiency. Again, the vapor flow should not be so high that when it escapes, when it passes through these perforations and escapes from this pool of liquid, it should not carry liquid droplets with it. It is known as entrainment. So this entrainment and weeping should be avoided. Okay, so now let us come to the what will be basically required, will be required to do in the lab. So let us start with this definition, review of this definition, relative volatility. You know that this is nothing but a measure of the differences in volatilities between two components. XA is the mole fraction of component A in the liquid and XB is the mole fraction of component B in the liquid. Okay, this value of the relative volatility is an indication of the ease of separation. So the relative volatility value is much greater than 1, the distillation will be easier. And for distillation to be feasible, it must be greater than 1. Okay, and higher the value, easier is the separation. So this is a typical three values I have chosen from books. So if you see ethanol and isopropanol, this consider this binary mixture, ethanol and isopropanol. Note that their boiling points are very close. 78 to 82, only 4 degrees Celsius. And that's why relative volatility value is also close to 1. It's not easy to separate through distillation. There may be other ways of separating it, but distillation is not that easy. Feasible, but value is close to 1, right? Now benzene and toluene, uh, better is, so you have an improved alpha value, relative volatility value is almost 30-degree difference in boiling. Now, if you consider hexane and paraxylene, so it is 68 versus 138, but it's almost 70 degrees Celsius difference in boiling point, wide to quite wide, right? Boiling points. So, relative volatility value is very high. Okay, so it's basically an indication of their differences in volatility, hence their boiling point, and hence the ease of separation. Okay. So like the knowledge of relative volatility is important for distillation. So you also need to have information on the vapor liquid equilibrium for the system. So the binary mixtures that you are separating, you need to know the vapor liquid equilibrium for that system. For example, if I am separating a mixture of methanol and water, I must know the vapor liquid equilibrium for this methanol and water system, because all we are doing is ideally, if the tray behaves ideally in bringing this liquid phase and vapor phase in equilibrium with each other, if that means when this vapor phase will escape a particular tray and the liquid phase will also escape that particular tray after mass exchange. If equilibrium was established, these two streams will be in equilibrium with each other. Okay, so if the tray behaves as an equilibrium trace or ideal trace, we know that at every tray equilibrium is taking place between the vapor phase and liquid phase. This will not normally happen because of the tray efficiency, but that's the limit, right, of heat exchange. That there is a limit of mass exchange. So we need to know the equilibrium relationship between the vapor phase and the liquid phase. So this is a typical data for vapor liquid equilibrium data for methanol water system at 1 atmospheric pressure. You know that this is pressure dependent thing. So this is how you know that this is how the vapor liquid equilibrium data are expressed. Can be expressed in table form or as well as this XY diagram. This diagram is popularly known as XY diagram, where in the horizontal axis you present the mole fraction of the more volatile component in the liquid phase, and on the vertical axis you present mole fraction of the more volatile component in the vapor phase. Note that those values will be lying between 0 to 1, right? Because since they are mole fractions, they will be lying between 0 to 1. And we also put this XY line, which is a 45-degree diagonal. So every point on this line basically represents X equal to Y. But every point on this line means that this X and this Y are in equilibrium with each other. So every point on this equilibrium curve represents an equilibrium vapor phase and liquid phase concentrations. Okay, so you'll find various types of this vapor liquid equilibrium curve. This is like more idealistic looking vapor liquid equilibrium curve, where it's much easier to separate. But this kind of curve shows that there is non-ideality in the system. So this is a more representative of non-ideal vapor liquid equilibrium data. So these are even I mean, more non-ideality is there, and in fact, basically, it gives you the azeotropic mixture, both these and these. Note that I told you that for distillation to possible, your vapor liquid your relative volatility must exceed 1. Okay, so at this point, you see x equal to y, right? Okay, so this point basically you will be able to separate through distillation. So this is the azeotropic point. Okay. Okay, so we'll briefly talk about McCabe-Thiele method. We'll briefly review the McCabe-Thiele method that we'll be using for finding out the number of distillation column for the experimental setup that we have in the lab. Before that, you can also do this, and we'll be doing this in addition to McCabe-Thiele diagram. There is this analytical expressions known as Pensky equation, which is based on certain assumptions. And this gives you the minimum number of theoretical plates that may be required. So note that these are based on these compositions. XD is the composition at the composition of the distillate. This is the composition of the bottom, right? So X, that means these are all liquid phase compositions. And this is the average relative volatility. Average in the sense that what you can do is you can compute the relative volatility, which is defined like this at the top and at the bottom. So this is at the top, this is at the bottom, and take geometric mean of these two. So this gives you the number of minimum number of theoretical trays. Okay. So now let me briefly review the McCabe-Thiele diagram for you. So let us first look at the nomenclature. Okay, how we represent these streams that are coming out of any particular stage. Let us focus your attention on any stage n. So any stage n, any stage n is receiving a vapor stream that is coming from a stage below it and receiving a liquid stream that is coming from the stage immediately above it. Okay. Now, these streams, the flow rates, this capital L represents the liquid flow rate, capital V represents vapor flow rate, X represents mole fraction of that liquid phase, mole fraction of more volatile component in that liquid phase, and Y represents mole fraction of more volatile component in the vapor phase. And the liquid stream and the vapor streams carry as your subscript the tray that where it is originating from. So this stream is leaving stage n, so it is represented as Ln. So Ln is the liquid flow rate. Okay, is the flow rate, molar flow rate of the liquid stream that is coming from the stage n. It will have composition Xn. This vapor is approaching stage n, so it is coming from stage n plus 1. If I call 1, 2, 3, if we start numbering from the top, so this vapor stream, okay, will be represented as Vn plus 1. So this is the molar flow rate of the vapor that is coming from stage n plus 1. Its composition will be Yn plus 1. The same thing will happen for this vapor stream that leaves stage n. It will be Vn and Yn. And the liquid that comes to here is Ln minus 1, Xn minus 1, because this is coming from stage n minus 1. So in one line, the vapor streams and the liquid streams will be designated, will be identified by the stage number from where it is originating. Okay. Now, if you remember that, so this is what happens, right? If you look at any particular equilibrium of any stage, we call equilibrium stage means theoretical stage. Okay, so at that time you consider that it is behaving ideally, so equilibrium will be established between the liquid stream that is living and the vapor stream that is living. Not the ones they are approaching, the ones which are living. So you can immediately figure out that the streams that are living, the vapor stream that is living and the liquid stream that are living, an equilibrium stage, that means an ideal stage, these two concentrations will lie on the equilibrium curve. Okay. Now we are also familiar with operating lines. What you obtain by doing mass balance around the rectifying section, doing another mass balance around stripping section. So these passing streams, right? The stream, the vapor stream that is leaving a tray and the liquid stream that is entering that particular tray, they are connected by the mass balance equation known as operating line. So the concentrations of these passing streams are represented by the operating line, and the streams that are leaving, since we assume that they are in equilibrium for an equilibrium stage or ideal stage, these concentrations, these two concentrations will fall on the equilibrium curve. So quickly, this operating line, so you take an so the section above the feed line is operating rectifying section, right? So draw an envelope around the rectifying section, okay, including you enclose the condenser. So this leaves, this enters, this leaves. So the total mass balance equation will be which enters, what enters V must equal what leaves because of steady state operation. We are assuming that these all distillation columns are operating at steady state. So this is the total mass balance equation. You can immediately write a component balance equation simply by multiplying these streams with their corresponding concentrations. There's mole fraction concentrations. So this is the total mass balance. This is the component balance. That means more volatile component A, mass balance in terms of more volatile component A. So this is the total amount of A that enters. This is the total amount of A that lives with this liquid, this, and this is the total amount of A that lives with this withdrawal stream. If you rearrange this, you will get this. Now you see this ln and vn plus 1. So yn plus 1 and xn, right? You see they are passing streams. Okay. Now for this entire rectifying section, we assume that these liquid molar flow rates are constant, vapor molar flow rates are constant. In that case, you can actually drop this n plus 1, etc. You can simply say L by V. Now, if you further use this relationship between L and V, which relates actually the reflux ratio LR, L by D, you will get this relation. So this is nothing but this, okay, after putting the definitions of the reflux ratio. This is known as rectifying section operating line. If you look at it on the XY diagram, this represents a straight line with R by R plus 1 as slope and 1 by R plus 1 as, this as intercept. Okay, this entire thing as intercept. So you can immediately plot this. So xd by R plus 1, see this is the slope. So this is the slope. So identify the point, these slopes, okay. And then this is the xd point, okay. You draw this. From this, you draw a line with this slope, or you can identify this point and identify the xd point, this point, right? The operating line has to satisfy that. So identify that xd point, the composition that is coming out from the top of the distillation column, draw a straight line. This will have the slope R by R plus 1. So this is known as operating line for the rectifying section. Exactly the same thing you do for the stripping section. take an mass balance equation around the stripping section. Exactly same. You get this as operating line. Okay. Again, you can consider this all the liquid flow rates in the stripping section is same. All the vapor flow rates in the stripping section is same. So this L bar by V bar can be used instead of putting M plus 1, etc. And using again these definitions, you will have equation for this stripping section. So again, it's a straight line. Okay, it's a straight line with a slope L bar by V bar. See, with the slope L bar by V bar. Okay, which is same as this. And we'll pass through these XB points. So basically from XB point, you draw a straight line with this slope. You'll have the stripping section operating line. Now, to complete the picture, you also have to look at what is happening at the feed plate. This rectifying section and stripping section operating lines do not take care of the feed line, do not take care of the feed tray. Okay. So rectifying section is the entire portion above feed tray. Stripping section is the entire portion below feed tray. But there is something else is happening on the feed tray which needs to be taken care of it by a separate mass balance equation, because another stream enters there. Now, depending on the type of depending on the thermal condition of that stream, whether it is partially vaporized or it is saturated liquid, superheated, etc., etc., you know, there will be different mass balance equation around the feed tray, because if it contains some vapor will go up. If it is entirely liquid, the entire liquid will come down. Whatever it is, perhaps you please recall that there is something called Q value, right, which is characteristic, which characterizes the feed condition. So based on that, you will have a Q line equation or the feed line equation. So this feed line equation will have different types of slopes based on the value of the Q. Q is the one which characterizes the feed condition. Now, to find out the number of trays in a distillation column in McCabe-Thiele method, please now do all these things that we just discussed. First, draw the equilibrium curve, draw the 45-degree diagonal, equilibrium curve, 45-degree diagonal, locate XD and XW. So XD is the top product composition, XW is the bottom product composition. Okay. Now at this stage, you can draw the Q line, that means feed line. So that will pass through ZF point, ZF point. ZF means composition of the feed. So ZF point will of course lie on this, all XD point, XW point, ZF point, all are on the X equal to Y line, right? 45-degree diagonal. So from this point, draw that Q line with the slope according to that equation, Q by Q minus 1. Compute the Q value, and with that slope, you draw this Q line. Now, this Q line actually passes through this point of intersection between these two rectifying section, and stripping section operating line. So from XD, you can draw this rectifying section operating line. How? You take out this point plus, so XD by R plus 1, that intercept. So that is done. Now to draw the stripping section operating line, you simply connect this XW point and this point of intersection between Q line and the rectifying section. Now you are done. So now what you have to do is, you know that you have to draw these staircases between the space that is available between equilibrium curve and the operating lines. You can start with any end. Let us start with, say, rectifying section, that top composition XD. So go on drawing like this, and when you cross this Q line, you start taking the stripping section operating line. So this way you continue till you cross the XW point, bottom composition. That means you have a tray which is basically doing the separation corresponding to the XW composition. So compute, just count the number of stairs, which represents the number of columns, which represents the number of trays. Now, what is happening in what will happen in case of total deflux is that under total deflux condition, you do not take out any product from the top, you do not take out any product from the bottom, and you also do not enter any feed to the distillation column. So whatever amount you have charged, okay, then you switch off the feed line, you switch off the top product line, you switch off the bottom product withdrawal line. So all the vapor that escapes from the top are condensed and sent back as reflux. So you can D equal to 0. So reflux ratio R by L by D is infinity. OK, because D is 0, basically very high reflux ratio. And then similarly, the bottom product is also B equal to 0, F equal to 0. So entire vapor that entire vapor that reboiler vaporizes this liquid stream is fed back to the distillation column. Now, under this condition, you will see that XD by R plus 1, right? If you consider that intercept XD by R plus 1 on the Y axis, okay, see that will come to 0. Like what will happen is both the operating lines, rectifying section and stripping section operating lines will collapse on this 45-degree diagonal. Okay, so you do not have Q line, right? So now you simply between XD and XW, you do the staircase computations. Now you can understand that you are now using the maximum space that is available between the equilibrium curve and the operating lines. These now serves both the purpose of rectifying section operating line and stripping section operating line. So your stairs will be the biggest possible in size. That means the largest possible mass exchange will be done in each tray. So and will be requiring minimum number of trays. So theoretically, minimum number of trays is possible only under total deflux condition. So it's basically a limit. It gives you the minimum lower limit. It practically won't do this because you are not going to take any product, right? But it gives you the minimum threshold on the number of trays that is required for performing that separation. You are causing this separation, right? Because you are doing this XD, right? XD is coming out from the top, XB is coming out from the bottom, but you're not withdrawing any product. Okay, so now what you will be doing is you will be given a liquid vapor mixture. Okay, you will be given a binary liquid. Okay. And so what we will do is we'll give the equilibrium data for the binary liquid mixture. And this binary liquid mixture, you will be separating under total deflux condition in the distillation column. So we have say in the past when it was possible to do experiments, from each tray or from alternate trays, it is possible to take samples. There are small pipes that are coming out from inside the trays to the outside. So it's possible to take out the samples. You can analyze them, so you can find concentration on each trays. I think data will be given for alternate trays. And also the top product composition, condenser composition, as well as the boiler composition. So top product, bottom product compositions. You will be finding out using that data as well as the equilibrium liquid phase vapor phase relationship. So equilibrium vapor liquid data, that means vapor liquid equilibrium data will vapor liquid equilibrium data will be given. The feed mixtures compositions will be given. Okay, the top product, bottom product, and composition of the trays, each trays will be given. Using these, you will find out what is the minimum number of trays that will be required for when the distillation column is operating under total deflux condition. Then you will find out. I mean, you will also be given how many number of actual number of trays are there in the existing setup. So you can find out that overall tray efficiency as total number of calculated trays divided by total number of actual trays. Total number of actual trays typically will be higher than the number of calculated trace. So the tray efficiency will typically be less than 1, and you have to report that tray efficiency value. Okay, so that is all from my side. Now TA will take over, but I'll just stop with a one line. Then this, it is this reflux ratio is a very important parameter for distillation column. So the you can understand the under total reflux condition you are using maximum possible value of the reflux ratio, right? The largest possible reflux ratio value. It's mathematically it is infinity. Similarly, you will have also minimum reflux ratio. So minimum reflux ratio gives to maximum reflux ratio or the maximum reflux ratio or total reflux gives you minimum number of theoretical trays required for that separation to perform. Minimum reflux ratio gives you infinite number of trays required. Okay, so your practical reflux ratio will be somewhere in between, of course, right? Now, there is something called optimum reflux ratio, which comes out from economic consideration. See what happens as you increase the reflux ratio, you need minimum number of trays. That means the annualized cost, okay, I mean the fixed charges on equipment, the equipment cost decreases, right? As you increase the total, as you increase the reflux ratio. But as you increase this reflux ratio, note that you will be handling more number of liquid, more number of vapors, right? So your annual charges, that means recurring charges for steam, cooling water, etc., will increase. Okay. So the steam cost will increase, cooling water cost will increase. So those such operating costs will increase. But minimum number of with increasing reflux ratio, the cost on equipment will decrease. So if you add these two, one is increasing with reflux ratio, another is decreasing with reflux ratio. If you add these two, you'll have this total cost curve versus reflux ratio, which will show a minimum. And this minimum is typically, somewhere between around 1.2, 1.3, 1.4 times the minimum reflux ratio that you have to identify. The minimum reflux ratio is, say, if this is the minimum reflux ratio, you see here the cost will be infinite because you need infinite number of trays. So this component is going to be infinite. Okay, so this is the optimum reflux ratio, and this is the one which you will be using for practical separation in industry. Okay, but for our yeah, for our experiment, you will be given data for operation under total reflux condition. So that's all from my side. So if you have any question, you can quickly ask. Otherwise, our TAs will now take over and briefly describe um, the experimental data and the experimental procedure. I have already briefed you, but maybe it may take 5-10 minutes to describe those things. Okay, so since there is no question, so yes, who will be present to? So TA, please
Yes, sir.
take
Sir,
over.
Gargi had some issue, so I will be sharing the screen and she will be speaking.
Okay.
Okay. Yes.
I guess Gargi has not joined yet.
Okay, Gargi might have some network issue.
Okay.
Yeah, see, I have already briefed. Okay, so please just present the data to the students. That will be enough.
Yeah.
So any of you, please take.
Yeah, this is basically the calibration data, this data that is being shown. So like the previous experiment only, you have to plot the refractive index on the y-axis and the volume fraction on the x-axis. So this is the calibration data like the previous one only. And like moving to the next one, yeah. So these are the datas that will be obtained for different rays like 1, 3, 5, 7, 9, 11, 13, and also for condenser and reboiler. So we will obtain this set of refractive indexes over here, and from the graph, so the graph, no, move to the previous one. So like the graph we obtained in the previous, using the previous data, the calibration curve, we will obtain the mole fractions. Like we will first take out the volume ratios, and then we will find the mole fractions using the densities. Okay. Now moving to the next, yeah. So this is the equilibrium curve. So equilibrium data. So x basically denotes the mole fraction of the more volatile component, that is ethanol over here, I guess. So and y is the vapor component only. So the mole fraction of the more volatile vapor component. And so this equilibrium data is basically used for plotting the McAfee curve. So we have to plot the McAfee curve using this data, means the equilibrium curve of the McAfee method using this data. Yeah, and moving to the next slide. Yeah, now in this experiment, the total reflux we will use the total reflux ratio condition. So basically D will be equal to 0. So the rectification line we will obtain is basically the straight y equal to x line over here. So, and this is the tray efficiency. Yeah, we will come to the tray efficiency later. Moving to the next slide for the, yeah. So first of all, we will plot the equilibrium curve, calibration data. We will find out the mole fractions of different trays for, and then we have to plot the McAfee diagram basically. So for plotting the McAfee diagram, we have used total reflux ratio condition. So D will be equal to 0 here. So you can obtain the rectification line from that. After that, also the feed we are providing here is liquid. So since the feed is liquid, Q will be equal to 1. So since you know the value of Q, you can obtain the stripping line as well. So now once you have the stripping line and the rectification line, also you know the equilibrium curve as you have provided you the equilibrium data, you can find out the number of trays by the McAfee method. So after that, after finding out the number of trays, you have to use the formula like in the previous slide. In the previous slide we have told out, we have given in the formula for calculating the tray efficiency. You have to calculate the tray efficiency accordingly from it, and also you can calculate you can use the Fenske's equation to verify that. Yeah, the Fenske's equation we also have provided in the previous slide for the number of trays. Right. Yeah, that's it. If you have any doubt, you can ask.
I will upload the PDF or the Word format of the whole data set and everything in the Teams now.
Yes, please do that. Yeah, I was going to do that. Plus, yes, please do that. Please, yeah, Nishant, please go ahead. Yeah, Nishant, are you doing that?
Yes, sir. Yes, sir. I'm uploading that.
Okay. So upload that. Where are you uploading?
Like the assignment.
Files. Okay, under the files, no?
Yes, sir. I can do that, or I can also give it as.
Okay, you do that. You put under files. Okay.
Okay. Okay. Yes, I'll do.
Under files. Let me do that. Put the assignment here.
Hello, good afternoon, sir.
Yeah.
Sir. Sorry, sir, I was having the.
Oh, okay. We have taken care of that.
So, sir, so. Could I
Yeah,
explain?
it's done. It's
Now.
done.
Okay.
Yeah, it is done.
Nishant, can you please upload the slide, please?
I have uploaded the assignment.
Assignment, no, the slide.
Okay, I will reshare it. Okay.
Sir, I'm sorry for taking everyone's time.
No, it is done. It is. You don't have to do anything now. It's complete.
Yes, Gargi, that has been completed. You need not present or explain again.
Not have to present again. It has already been presented.
Sir, I've uploaded it in the file section, so you
Okay.
can
You
create.
have uploaded, no?
Yes,
Just
sir.
a minute.
Sir, if it is needed, I can explain it once more in 5
There's no
minutes.
need. Nobody is no already Arnav and Nishant has done that.
Yeah, like if anyone has any doubt, they can
If
ask.
anyone has
in
any
the
doubt,
calculation.
then yeah, then you can then only. There's otherwise no need. Okay, I think there is no doubt. Please check, any of you please check this assignment 3 also. Now I have put the same thing I have put as assignment 3. Shame data sheet I have put as assignment 3 and your due date is 16th February. Assignment 2 is due today. That means we are calling these experiments as assignment. That's okay. Okay. So if anybody has any question, can ask now. Otherwise, we'll leave meeting. Okay, fine. So we'll stop. In your yeah. Okay, we'll stop then. Yeah, Professor Hari Krishnan will stop, right?